Good morning, everyone. I am Sai Krishna from Computer Science Engineering AML Section C. Today's subject is data structure. Concept dream is caring for ecological asset in smart cities. Introduction to Tree Management Information System. MIS. A tree MIS is a data-driven system designed to monitor, analyze, and manage urban tree population using structured data models and real-time sensors. It generates GIS, IoT devices, and machine learning to assess tree health, growth patterns, and environmental impact within smart city frameworks. The system leverages hierarchical data structures like trees, graphs to represent spatial relationships and dependence among urban flora. TRIMS supports decision making for urban planners by providing predictive analytic in canopy coverage, carbon sequentials, and stormwater mitigation. Forms a critical component of sustainable urban infrastructure, aligning with SDG 11 sustainable cities and communities. Role of data structure in TRIMS. Tree data structures are used to model hierarchical relationships such as parent-child branches, species taxonomy, spatial zoning in urban forests, binary search trees, enables efficient query of tree records based on attributes like species, age, or GPS coordinates with zero log and average case complexity. Graph structure represents adjacency and connectivity between trees, supporting pathfinding algorithms for maintenance, routing, and disease spreading modeling. Hash tables store metadata, example health scores, inspections data with 0 1 average lookup time, enabling rapid access during field operations. Priority queues manage maintenance tasks based on urgency, using heap structure to dynamically record service requests. Tree representation in computational models. Urban trees are modeled as noted in a graph G equals to VE, where V represent individual trees and E denotes spatial ecological relationships. Each node stores attributes species, string, age, integer, height, float, health, index 0 to 1, and GPS coordinates lat long. Tree hierarchies use rooted trees to represent canopy layers, with root as trunk and children as primary branches, enabling structural analysis. Adjacency matrices or lists encode proximity-based interactions such as root competitions or disease transmission, risk between neighboring trees. Spatial interaction via arteries or quadries accelerate range queries for locating trees within geographic boundary. IoT sensor integration and data acquisition. Soil moisture, temperature, and light sensors are developed at tree bases, transmitting data via LoRaWAN and NB-IoT to a central server. Denometers measure trunk diameter changes with micrometer precision, providing growth rate data, data delta D by delta T used in health assessment models. Multispectral cameras on drones capture NDVI, normalized difference vegetation index. NDVI equals to NIR minus red, NIR less red, indicating photosynthesis activity. Uh, Accelerometer detects wind wind-induced sway with frequency analysis used to estimate structural integrity and risk of high failures. Center data streams are time-stamped and ingested into time series database like InfluxDB for real-time monitoring and anomaly detection. Health assessment using machine learning. Supervised learning models, example random forest, SVA, classify tree health using features, leaf discoloration, bark integrity, and growth rate. Training data is labeled by herborist and labeled images and sensor readings, forming a feature vector X equals to Rn. Model performance is evaluated using precision decoded F1 source with class validation to prevent a overfitting Bell's dataset. Anomaly detection via isolation forest or autoencoders identifies outliers in sensor data, flapping potential disease or question investigation. Model outputs feed into a decision engine that assign a health score H. Update dynamically as new data arrives. Carbon sequential estimation. Above ground biomass AGV is estimated using allometry equation AGV P equals to P into D square into H into F, where D is diameter, H is height, E is wood density, and F is form factor. Carbon content is derived as C equals to AGV into 0.5, assuming 50% of dry biomass is carbon following IPCC guidelines. Annual sequential rate delta C by delta T is computed by differencing carbon stocks over time integrating into city-wide carbon accounting systems. Uncertainty is qualified using Monte Carlo simulations, propagating errors from measurements and model parameters. Results are visualized in dashboard showing cumulative CO2 equivalents, TCO2e, sucraged per district or species. Stormwater runoff vegetation modeling. Tree canopy interception reduce runoff volume. The interception capacity IMM is modified as I equals to A into LA into P, where LA is leaf area index and P is precipitation. Root system enhance infiltration rates. Hydraulic conductivity case CM by HR is estimated from soil type and root density using decay log Q equals to minus K delta H SWMM. Stormwater management model integrates T parameters to stimulate urban hydrology under various rainfall scenarios. Reduction in peak runoff is quantified as delta Q equals to Q naught minus Q1, where Q naught and Q1 are flows without entry with canopy respectively. GIS layers overlay tree location with drainage networks to prioritize planting in high runoff zones. Spatial query and index techniques. R trees index 2D spatial data, example tree location, enabling efficient range and nearest neighbor queries with zero log and complexity. KD trees partition space recursively along axis, supporting fast KNN searches for identifying trees within a radius for R of a point. Quiet trees subdivide regions into four quadrants, ideal for visualizing trees density at multiple zoom levels in web-based mesh dashboards. Spatial joins combine tree data with joining maps using algorithms like PlaneSweep to identify trees in protected or high-risk areas. Index maintenance includes rebalancing and node splitting to preserve query performance as the dataset grows. Predictive maintenance and risk assessment. Failure risk R is modeled as R F equals to H